You know what team you're on? We were talking about populations last time and how populations change over time. And these are what are called survivorship curves. You might see these on an AP test.
Okay.
Yes. A survivorship curve works like this. Let me just give some examples. This top curve right here, on the x-axis is the percent of lifespan. On the y-axis is the number of survivors. The way this top curve works is that most organisms in a population like this survive to the end of their lifespan. The death occurs after the midpoint. So if you have 1,000 individuals in a population, almost all of them are living near 100% of their lifespan. The human population is like that now. Most humans live to old age, and then a lot of them die at the very end. So that is what we call a type 1 survivorship curve. And they show bluegrass seems to be like that. Most bluegrasses survive, and then they kind of die in old age. I don't know how old that is for a bluegrass. Maybe it tells you in the reading. Mosquitoes, though, have just the opposite type of life. Most of death of their population occurs at a very young age. Mosquito larvae, mosquito babies, die very easily. They live in water, standing water, or ponds or streams, and they're eaten by fish and all sorts of things. And most of them don't make it to adulthood. So you see, out of 1 million baby mosquitoes, only, less than 100 are surviving for very long at all.
Why is there a bomb? Why does it go off?
That's probably experimental error, or just randomness. And whenever you're actually counting numbers of individuals, it's not going to be a perfect, nice, smooth curve. But have you ever seen a graph like that? That's called a logarithmic graph, where it goes 0, 100, 10,000, 1 million. It's not going up in a nice orderly fashion. It's jumping by powers, by 10 to the second power each time. Y'all seen graphs like that? So that point right there would not be 50. There's 0, there's 100. You would think right in the middle would be 50. But there's 100, there's 10,000. Right in the middle is not going to be 5,000. 5,000 is going to be further up, because as you go up, it intensifies as a log. Y'all have these in math? Something to that? Okay, so in this, lizards are just kind of even. Some of them die at a young age, some of them die at an old age. It's kind of an even distribution. And here, these curves, that's a perfectly straight line, and that's a perfectly nice curve. So I would guess, just by looking at these, that this was an actual sample, because this graph is bumpy. Christian, you were kind of asking about this. This graph looks bumpy, so that was probably an actual sample from an experiment. And these nice smooth curves are probably just estimates or lines of best fit or something like that. We call those survivorship curves. So what would you guess whales would be like? Do you think? Type 1, type 2, or type 3?
1.
Type 1. Probably whales are more like type 1, more like humans. What would you guess roaches would be?
Type.
Probably type 3, yeah. I don't know. I mean, usually they don't fit exactly as type 2. They say lizards do, but I don't know.
They're just kind of, I've never heard
Yeah,
of it.
it's kind of weird. There'd be a lot of populations in between the two. These are more just reference curves that most populations probably don't perfectly fit any of those three. They have names for type of strategy in life. They can call you what's called an R strategist or a K strategist. R versus K strategy. R strategist means you have a high growth rate. R means growth rate. These are organisms that expend a whole lot of energy on reproducing. Thus the R. And they just can cough out 1 million kids. Like roaches, you know, they can have lay thousands of eggs. And they just hope that some survive. They don't really take care of them or anything.
High birth rate? Is that it?
What's that?
High birth rate?
High birth rate.
Okay.
Fast. They grow really fast. They get to maturity quickly. They don't live for very long. Weeds are like this. Have you ever heard of annual plants? That means they live 1 year is all. They grow, they put out a bunch of seeds, and then they die. And hopefully some of those seeds will survive because they make so many of them. Little dandelions and things.
So it's like kind of like a pine tree?
That's the R strategy. Well, no, a pine tree is a little bit different because pine trees reproduce every year, year after year. They live for real long lifespans. Pine tree can live for 100 years or more. So it's not really a perfect R strategist. R strategists are more like those little weeds that only live a real short time.
Since like all the pine trees are like releasing their pollen cones now, is that like the end of pollen season?
Yeah, the pollen will land hopefully in a pine cone on another pine tree and fertilize the egg in there, and then a little seed will fall out in a few months.
So I mean, like they're releasing, or like at least when I walked out to my car this morning, it was like completely covered in those little like fluffy looking.
Those are the pollen cones.
Right, but
yeah.
Does that mean it's like closer to the end of pollen
Yeah.
season?
Mm-hmm. Yeah. They're done. Once they release all their pollen, they just fall off the tree. So we call those R strategists that make a lot of organisms, and their populations can really go up and down. You know, if there's a time where it doesn't rain for a while and they don't have enough water, they'll all die, except for maybe a few surviving eggs and stuff in the sand. You know, or you could have a freeze that kills almost every mosquito, and then they'll all come back real quickly. You ever notice this? If you were to graph the population of these R strategists, they'd go up and down very, very quickly because just a few can reproduce and make a lot when the conditions are right. We call those R strategists. K strategists are different. K strategists have long lifespans. They usually have few kids. And in the animal kingdom, they will really put a lot of energy into protecting their children. Most vertebrate animals are like this. Humans are like this. You only have a few kids. Spend your energy protecting them. Instead of having 1,000 kids and just hoping some survive, you have a few kids and you make sure they survive. We call those K strategists. And they call them K strategists because K stands for carrying capacity, which I'm about to show you a growth curve that shows you what that means. But these organisms tend to live at the carrying capacity of their environment. Their populations don't go way up and down. They stay stable at usually as high a population as the environment can support. And they're able to live through hard times and adapt and survive. So that's kind of two kinds of strategies. Look at all these people. Look how happy they are. You never see, people aren't really that happy. Okay, so let me show you these age structure diagrams. This is another graph that you might have to figure out how to look at. So we have three types of age structure diagrams. We've got this kind that you would see in a developing country that has a population that's going way up. And this is kind of a stable population, and this is a population that would be going down. We don't see a whole lot of these in human populations. But age structure diagrams. No. So how you read this is at the bottom of the diagram. Hold on, let me see if I can find something here. Shows it a little better. Oh, here we go. This is good. So here it shows the age structure diagrams for human populations, and you see this axis over here is the age of the humans, and so if this shows, okay, this first bar right here are 0 to 4-year-olds, babies, and it shows how many millions of them there are in this population. On the left side of the graph are, what's that symbol, do you know? Males. And on the right side are females. So for babies born, for this population, there's about 280 million males and about 260 million females. I guess that's a lot. I don't know what country this is. Oh, it's all the less developed countries added together. So we're talking about places like India, Africa, and countries in Africa, poorer nations tend to have. If you look at this, so these are all the kids on the bottom. We say the pre-reproductive years. Here in the middle, all the reproductive years and post-reproductive years on top. So, young people, middle-aged, and old people. These people are able to reproduce, able to have kids. So, pre-reproductive, reproductive, and post-reproductive. And you can see it's thick on the bottom and thin on the top. That tends to happen if the bottom column is thicker than the middle column. That means the people are, on average, having more than 2 kids per couple. They are having more kids than themselves, so the population is going to grow. Does that make sense? And so if a population is having more kids, in the future that population will be larger. So over time, the people die, so it gets less and less as you go to the top. That's why it's small on top. Does that make sense? And you can see the women's side is a little bit wider than the men's side because women live longer than men. Isn't that interesting? In actuality, more men are born than women. Anyone know why that is? That's an interesting.
Isn't that because like the Y chromosome is smaller?
You got it. Good job, Brandon. The Y chromosome is a little bit smaller than an X chromosome, so those sperm are a little bit heavier, and less of them get to the egg. Isn't that interesting? But you can see in the developed countries, these are like, the developed nations, Europe and America, Japan, nations with more money. You can see they tend to have less kids. And so this type of country is not going to be growing in size. A lot of people would look at this and go, well, this means the population problem is obviously the lesser developed countries. And that is true if you count numbers. But in a more developed country, each person uses a lot more resources. And they say 1 American has the same impact on the planet as 30 people from Africa. That's how much stuff you use. You drive around in your cars. We're burning electricity in this building. Every time you eat something, you throw away the wrappers and stuff. They don't do this in less developed countries. They don't have their food in wrappers at all. They don't have as much trash. They aren't burning gas. They walk places so that it doesn't impact the environment as much. So that's kind of an interesting thing to the population problem. There are problems in numbers with the less developed countries. There's problems in using resources in the more developed countries. Problems both ways. Wow, dead animals.
It's an aggressive looking deer. That's awesome.
Yeah, that one's not. But that. Okay, so let's talk a little bit about these growth curves. You're going to have to know these, be able to read these growth curves and answer questions about them. So here's how a population starts. A population, if you were to graph the growth of a population, let's say we got a couple of insects or something. Let's do it even more simply. Let's say we put a bacterium in a lab dish, and we let that bacteria multiply. If it was an E. coli bacteria, they divide their cells once every 20 minutes. So you start with a population of 1. 20 minutes later, how many do you have? And 20 minutes later?
4.
Then what?
8.
Then what?
16.
Okay?
2.
Very good.
64.
Okay.
28.
128, 256, 512, 1024, 2048. Okay, so let's just make a graph of that real quick. So on the bottom, let's do time, and let's do it in hours. How many hours has gone by here? Can you count that for me? If it's 20 minutes,
4
20,
hours.
20, 20, that's 1 hour. 20, 20, 20, that's 2 hours. 20, 20, 20, that's 3 hours. Whoops, I skipped one, didn't I? Skipped that one. That's 3 hours.
3.5 or 3 and
20,
2/3.
20, 20 is 3, and then
3.6.
20. Let's do one more. Let's go to 4,096. You want to? Why not? We're making our graph. So that's 4 hours. Are you getting this, fam?
Yeah.
For our viewers at home? Viewers at home. Going to school at home. Who would have guessed it? Okay. So, time and hours, and you want to do population over here? So, we'll start with 0 on the bottom, and what's our highest number? 4,096. So, we'll do 4,000 up here, and give a little room on above that, and so I'll just do 1,000, 2,000, 3,000. You like my graph? I'm an EGM, expert graph maker. How should I do time on the bottom? How many total hours?
4.
Okay, you want to go to 4 hours? Start at 0, right? And so, I don't know, you have 1, 2, and 3. Last time I tried to count, that's how it went. So, times 0, how many organisms do we have?
0.
1. Start with 1. And then at 20 minutes, we've got 2. Where would 2 be on this graph?
Like right next to
Still be very low, wouldn't it? And at 40 minutes, we've got 4. That would still be quite low. And at 1 hour, we've got 8. That would still be quite low, way less than 1,000. And at an hour 20, we've got 16. That would still be quite low on my graph. In an hour 40, we've got 32. That would still be quite low on this graph. And at 2 hours, we've got 64. That's still rather low on this graph. Can you see how we've called this the lag phase. The population is slowly growing, but it's not really jumping up quickly. Then at 2 hours and 20 minutes, we've got 128 here. And that's a little bit higher on my graph. Still not near 1,000. And then 2 hours, 40 minutes, we've got 256. What's that? Yeah, still pretty low. But then 3 hours have passed. We've got 512. That's about halfway to 1,000 there. And then 1,024 at 3 hours 20 minutes. So now we're right here. And then 2,048 at, it's way up here at 3 hours 40 minutes. Just kind of eyeing this. It would be better if I had lines on it. And then all of a sudden, at 4 hours, it's at 4,000. Bam. You see, we really moved a lot at the end there. Are y'all with me? And if I had a computer draw this curve, it would be nice. Oh, that's almost computer worthy there. Y'all don't know this, but I'm actually a robot. Built to teach. Isn't that good? That's a pretty good curve. So there we go. That is the normal. Every population does this. I graphed bacteria, and you say, well, humans aren't like bacteria. You want to see the human population growth over the last, whatever, 100,000 years? No, that's not it. Look at that. Whoop. That's human population. Just like that. Isn't that amazing? Going back to 1750, there were 1 billion people. Today, there's over 7 billion. And what's it going to do? We don't know. We call this exponential growth. Here's the deal with exponential growth. Exponential growth cannot continue unchecked. It has to end somewhere. And so growth will occur, we call it exponential growth, in this kind of J-shaped curve. See, it's shaped like the letter J. But it cannot continue like that forever. It will level off. And that's just because you run out of resources. And we reach what we call a stable equilibrium phase. At some point, it'll have to level off. And it just depends on how much resources. Even the bacteria in the lab dish will run out of food. And the population will level out. They'll start crowding themselves. They'll basically start to drown in their own waste. Doesn't that sound like a bad way to go out? Drowning in your own waste?
That's really gross.
That's what pollution is. You ever heard of pollution? That's our own waste. Pollution wasn't a problem when the human population was real small. You just threw your crap out wherever you wanted to. You know, just throw it in the woods. You got an old car? Just put it in the woods. There's no woods anymore. Somebody living in the woods. It's their land. So you start polluting, and that's exactly what's happening. And what's going to happen is the human population will level out, just like all populations do.
When do you think that'll ever happen?
They don't know. It looks like it's maybe just starting to, just right there, starting to go right there. So we'll probably be able to go up a few billion more, but it won't be like the last couple hundred years. We won't be able to accelerate like that. There's just not enough room on the planet.
Well, could it be that it doesn't level out until it's too far gone? Like, is that a possibility?
Well, it is, and and that also actually happens in natural populations, it'll go above this dotted line. This dotted line, by the way, you have to know, it's called the carrying capacity. Carrying capacity. It's how many organisms that an environment can sustain. And in actuality, the population will go above the carrying capacity. That means there's too many organisms for the area to handle. And so what it'll do is it'll go above that dotted line, and then it'll dip down back below because there'll be a lot more deaths because of not enough food, too much waste, and the population will drop back down. And then when it's below, then there is enough food to support, and then it'll go back above. And what happens is you just see kind of we continue this over this way, we see a curve that just kind of keeps going above and below the carrying capacity like that. When it's above the carrying capacity, times are bad and there's not enough to go around, and then it'll drop below, and then times are good and there's enough food for everyone, and so there's a lot of reproduction, and it goes up, and it just kind of, populations just do that over time. And so those K strategists that I talked about earlier, K strategists do like this. They hang out around the carrying capacity. Their populations do. R strategists tend to be more up and down. Suddenly the population can go way down, and then suddenly it can jump back up. The K strategists tend to hang out around the carrying capacity like that. And we're certainly K strategists. But you see this in all populations. You see a lag phase when it takes time for the numbers to really get going. This exponential growth that goes up, and then a deceleration, and finally a stable equilibrium when there's just not enough substance to go around. So the book talks a lot about those kinds of curves. And it talks about examples. Here's a real-world example of reindeer from some island up, I don't know, around Canada or something. Look, they were introduced to this island. Their population went up over time. Scientists were keeping track, and they actually, suddenly they had no food left because reindeer eat lichens, and lichens grow very slowly. And normally, a reindeer herd would just go somewhere else, would migrate to somewhere where there's more lichens, but they were stuck on an island. They couldn't migrate. And so their numbers all of a sudden just dropped to nothing. And that can happen if you have nowhere to go. So if you talk about the human population on Earth, if we just suddenly deplete all our resources, we could be, you never know. That could happen like that happened to the reindeer because we don't have anywhere else to go but this planet. It'd be nice if we could go to Mars or something like that. That was an interesting case study that they talk about in the reading. So I'll talk about that later. Read tonight about exponential growth and these growth curves, carrying capacity. You're supposed to read through 43.3 and 44.3 and 44.4. And I got a little more to talk about from 44.4. I haven't quite finished it, so we'll have to do it next time. Okay?
Okay.
Ah, what great timing. Did you turn it off? You know how to turn it off?
We have a last one.
We'll just